Why is it in compression? Okay. So before we break anything down, right, it's important to make some assumption over here. Okay, so we are going to assume analysis is for trust member. Now, when we declare it's a trust member, what do we actually mean? Anyone? Okay, if we assume that this is a trust member, okay, or member AC and BC are trust member, what do we actually mean? Right? You have to step back and okay, we're gonna assume trust, but what does it actually mean? Anyone want to make a guess when we assume it to be trust analysis? You can Google and see what happened. Okay, you can static. Yeah, this we are doing. This is 3803. Okay, this is not 2Q04 SAM. Okay, it's static. So what do we mean by when we do trust analysis? Okay, is doing for trust analysis. Okay, we assume that members AC and BC can only withstand axial loading. Okay, so all the load that are transmitted are in the axial direction. That's all. Okay, so I'm now going to break this down. Okay, by using method of joints. Okay, bear with me regarding this term can only withstand axial loading whenever we do a thrust analysis. Okay, bear with me. So now we are going to apply okay method of joint. And we are going to apply method of joint at point C. Okay, we're going to see what is going on at point C when we do method of joint. Okay, so we do method of joint. We know that at point C, right? The we have a load T. Okay. Next, I'm going to draw green lines. Okay. And I'm going to draw another one at an angle. Okay. So this green line still the same like what we had before. This green line represent the centroid for member B for member BC. And this green line is for member AC. Okay. So I'm going to do a multi-body. Okay. So this is our member BC. And the next one over here, this is for our member AC. Okay. So all the forces has to be acting along the green line. Okay, for AC, right? The forces has to be acting along the gradient green line or slope, whereas BC has to act on the horizontal green line. Okay, so by looking at what we have now, right? Member BC, okay, member BC cannot, so if I'm going to call this component X and Y, okay? So for member BC, or for this line over here, can only take forces in the what direction? X direction. Okay. Because it's running horizontally, right? It cannot take any vertical direction. Whereas the other one, the one on the slope, can carry forces in both X and Y directions. Okay, because it's on a slope. All right. Okay, now let's look at point C now. Okay. At point C, we have a force going up. The only member that can take this vertical load is member AC, because member AC is the only one can take forces in the Y direction. So in that context, right, over here, we know, okay, we know from here, this will be our ACY. Why is it coming down? It's because of what? Newton's third law. Action equal to reaction, semi-magnitude, different direction. So the P now, right, is preventing from going up because of ACY. Okay. So unfortunately, member AC is on a slope. Knowing that it's a vector form, we know that over here, this has to be our ACX. So in this context, we know that the direction from here to here, this is our F what? AC towards point C. And then later, when we apply Newton's third law, this goes in the opposite direction. This will be our FAC. And when that's the case, remember AC, this is in compression. So if you look into the chat, okay, some of you know that AC is in what? Compression, for that reason. Now, BC is also taking load. BC is taking load now is because of what? It's because of ACX. Oops, sorry. Because now we have a what? We have a ACX, right? So without BC, right, ACX will push point C towards the right. Yes or no? So in order to counter that, over here, you need to counter, and this is known as your BCX. Okay, so the BCX is going towards the left to prevent or to counter ACX. Okay, then after that, you apply Newton's third law, action equal to reaction. This is your FBC. So in this context, you can see FBC is pulling away from member BC is under tensile. So when that's the case, again, I highlight you in anything in under, not anything, but usually where it has compression load, we have to deal with buckling what? Analysis. Okay, BC, member BC will never fail by Barclay. Okay. Okay. So what we have learned so far is how to construct a multi-body free body diagram, and also how to predict the reaction forces. Okay, just by applying Newton's third law. Okay, right. So this is again a quick recap. Uh, somewhere in 2P that you have done this before, but I know some of you have done 2P a while ago. Just to give a quick refresher's course on structure analysis in terms of truss member. Okay. Now, the next thing that we're going to do is we are going to look at the deformation pattern. Okay, in compression loading. Okay, so we know that. Let's focus on compression loading. So now, if we have a structure now, and this structure whenever I draw a line, this is our centroid. Okay. So this is a structure that we have. And then on this structure, what is going to happen is we have a compression load. This is exaggerated. Okay. And then our transformation over here. Then we have a load. Okay. And then we know that over here we have a A, which corresponds to our cross sectional area. Okay. And because of the load that is applied, okay, initially this is our L naught, and now this is our L1, right? So over here, this is our delta L. Okay, that's our delta L. So if we were to look at deformation, without buckling, okay, the deformation without buckling, okay, is what you see is the change in L is equal to Py L naught over AE. Okay, and A is a cross-sectional area, L naught is the original length. Again, down here, E is our Young's modulus. Okay, now, and then the stress, right? The stress in the y direction is equal to Py over A. And we are aware that Py is, I'm going to write the minus sign here, because it is under what? Compression. Likewise, the delta L is in what? Minus. Okay, the negative sign declare is under what? Compression.